Okay, today we're going to be talking about something called particle motion. And particle motion essentially is the relationship between a particle's position, that particle's velocity, and that particle's acceleration. And so before we even get into some problems, let's understand some vocabulary. The displacement of an object is simply the total change in its position. And that is usually denoted with the letter S, S of t. So let's say I walk, or let's say I drive from here to Houston and back. Even though my total distance traveled may be 400 miles, my total displacement is 0 because my starting position and my ending position is still the same. So that's displacement. Now, average velocity is nothing more than the total change in your position divided by the total change in time. So if I traveled 200 miles and I traveled for 4 hours, my average speed was 50 miles per hour. I think that's pretty easy to understand. Now, the instantaneous velocity is how fast was I going at a specific time. So let's say at 2:37 p.m., exactly how fast was I going at that time? And that is denoted with v of t. Okay, positive velocity means you're moving in the positive direction. If you're on a number line, that means you're moving to the right. If you're on a y-axis, it means you're moving up, and vice versa. Negative velocity means you're moving backwards. All right. Speed is the absolute value of velocity, which means it does not have a sign. So you do not say that I am going negative 45 miles per hour. No, you just say you're going 45 miles per hour, even though you may be traveling south on 75, US 75 expressway. So speed does not have a sign, it just has a absolute value or a magnitude. Acceleration is the derivative of the velocity. All right, so the idea is that you have S of t, and then the velocity is the derivative of the position. And the acceleration is the derivative of the velocity, which is by default the second derivative of the position. And so these are the relationships that you're going to need to use for the next few problems. Okay, example 3. We are going to skip examples 1 and 2. You can get those off of the notes from my website, but we're going to jump right into particle motion. Example 3. A dynamite blast propels a heavy rock straight up with a launch velocity of 160 feet per second. It reaches a height of S of t. So this is the position of the rock at any time. How high does the rock go? Okay, so in order to find that, we need to understand that if a rock, let's just say a rock is thrown up in the air, then it's going to reach its maximum height and then it's going to start to come back down. At the point where the rock reaches its maximum height, the velocity is 0, because as it's going up, the velocity is positive, and as it's going down, the velocity is negative. So at the very instant where it reaches its max, the velocity is 0. That is consistent with what we've been learning in class, where at a maximum point on a graph, the slope is equal to 0. So how high does the rock go? Let's take the derivative of this. So let's say v of t, which is equal to s prime of t, the derivative of the position, is 160 minus 32t. Taking the derivative by power rule. So what we want to do is we want to set that equal to 0 to figure out the time when the velocity equals 0. So we set that equal to 0 and we solve it for t and we get 5. So 5 seconds after the blast occurs, the velocity is 0, which means it reaches its maximum height. Now, how do we figure out how high it goes? We need to take that 5 seconds and plug it into our position, because now we're looking for the position of the particle at a certain time. So we will say S of 5 is equal to 160 times 5 minus 16 times 25. And the answer that we will get is 400 feet. All right. Now, letter B. What is the velocity and speed of the rock when it is 256 feet above the ground on the way up? Okay, so what is the velocity? So the first thing we need to do is we need to find the time when the rock is 256 feet above the ground. So that's involving the position function. So we're going to plug 256 in for the position, and we're going to solve this for t. So let's go ahead and factor this. So negative 16t squared plus 160t. I'm going to actually move the 256 to the other side. And then I'm going to change all of these. Actually, you know what? I'm going to divide by negative 16. That's what I'm going to do. Divide by negative 16. When we do that, we're going to get t squared. And this is going to give us a negative 10t. And then this is going to give us positive 16 equals 0. So we factor this, and we get t minus 8 and t minus 2. So that gives us 2 times 8 seconds and 2 seconds when the rock is at a height of 256, obviously on the way up and then on the way down. So it asks you what is the velocity and the speed of the rock when it is 256 feet. So once again, we take these 2 times, but we're going to first use for when it's on the way up, so that would be 2 seconds. We're going to plug that into our velocity equation that we found in part A, and so that's going to give us, I'm running out of room here, so let me erase some things. Let me erase this to create a little bit more room. And so that's going to give us V of 2 is equal to 160 minus 32 times 2. So that's going to be 160 minus 64. That's going to be 96 feet per second. And then V of 8 is going to be 160 minus 32 times 8. And that is going to end up giving us, let's see, 32 times 8 is 16. And that's going to be 25. So 160 minus 256 is going to be negative 96 feet per second. The fact that it is negative lets us know that it is on its way down. Okay, what is the acceleration of the rock at any time t? So acceleration is the derivative of the velocity. So all we need to do is take the derivative of our velocity equation. And so the derivative of 160 is 0. And the derivative of negative 32t is negative 32 feet per second squared. That makes sense because that is the acceleration constant of gravity. So things fall at 32 feet per second squared. When does the rock hit the ground? The rock hits the ground when its position is 0. So we're going to plug 0 into our position function, 160t minus 16t squared, and solve for t. So I'm going to factor out a 16t, and that's going to give me a 10 minus t equals 0. Let's check that. 16t times 10 is 160t, and 16t times negative t is negative 16t squared. Set both of these equal to 0. We get 2 times t equals 0 and t equals 10. And clearly the rock starts on the ground and then it ends on the ground 10 seconds later. All right, example 4. A particle moves along a line so that its position at any time is given by this function. Find the displacement of the particle during the first 2 seconds. So, if we need to figure out the displacement, we need to know where this particle has started and what its position was when it ends. So we need S of 0, the starting position, and we need S of 2, the ending position. So to get the starting position, we simply plug 0 into the position function, and we get 3. To get the ending position, we plug 2 into that same equation. So 2 squared is 4, minus 4 times 2, which is 8, plus 3. So negative 4 plus 3 is a negative 1. So the total displacement would be 4 units. Actually, we could say 4 meters. 4 meters. And I guess you could say negative, but essentially it moved 4 meters. All right, find the average velocity of the particle during the first 4 seconds. Average velocity. So that's going to be our total change in our position. So our total change in our position divided by the total change in our time. So during the first 4 seconds, that means we need S of 4 minus S of 0. Let's interpret that. The position of the particle, 4 seconds at the ending time, minus the position of the particle at the starting time will give us the change in its position, divided by the total change in time. Well, that's just 4 seconds. So S of 4 is going to be, let's see, 16 minus 4 times 4 plus 3. So that's going to be 3. And minus the starting position, which is also 3, divided by 4. So 3 minus 3 is 0. So 0 meters per second. So essentially, because the displacement or the position of the particle did not change during the first 4 seconds, that means that the average velocity of that particle was 0. All right, examples C, D, and E. Find the instantaneous velocity of the particle when t equals 4. So now we're interested in figuring out how fast is this particle moving exactly at 4 seconds. So v of t is equal to the derivative of the position function, and that's going to be 2t minus 4. And now we're interested specifically in v, actually not v prime, we're interested in the velocity at 4 seconds. So that's going to be 2 times 4 minus 4. That's going to be 4 meters per second. Find the acceleration of the particle when t is 4. Well, acceleration is the derivative of the velocity, which is also the second derivative of the position. So if we take the derivative of our velocity, we get 2, which means no matter what time the particle is in its flight, the acceleration is going to be constant at 2. All right, so we want to describe the motion of this particle. At what values of t does the particle change directions? Okay, so let's talk about that. A particle changes directions when its velocity is 0. So you have a particle, maybe it's moving on a number line. So let's say this is our number line. And let's say you have a particle, and it is, let's say it starts here, and it's traveling this way. And then it starts to reverse its direction and go here. When it changes its direction, its velocity is 0. And let's say it gets to here, and then it changes and goes backwards that way. That point is going to have a velocity of 0. So basically what we need to do is we need to take our velocity equation and set it equal to 0. So 2t minus 4 gives us 0. T equals 2. So we know that it changes directions at 2. But now the question is, which way was it going before it changed directions, and which way is it going after. So we're going to put this number 2 on our number line. We know time starts at 0 seconds, so we have to plug in a number between 0 and 2, let's just say 1, into our velocity equation to see if the velocity was positive or negative in this time interval. If the velocity is positive, that means the particle moved to the right at the very start of its motion. If the velocity is negative, that means it started moving left. Let's see what it is. Let's plug in 1 into our velocity equation, and we get 2 minus 4, which is negative 2. So the velocity is negative. Let's plug in a number bigger than 2, like 5. 2 times 5 is 10, minus 4 is 6, so that's positive. So we know that the particle, as soon as the stopwatch started, it was moving left for 2 seconds, and then it moved to the right for the rest of its flight. So you will need to say that it starts moving left because the velocity is negative. Then at t equals 2, it moves right. Something like that is a sufficient definition or justification. Okay, example 5. Suppose the graph below shows the velocity of a particle moving along the x-axis. Justify each response. Okay, so which way does the particle move first? Well, we already established at the beginning of this lesson that when the velocity is negative, the particle is moving backwards. When the velocity is positive, the particle is moving forwards. So we have to look here and see that when the particle starts moving, the velocity is negative. Now, when I say negative, I'm not referring to the slope of this line. I'm referring to the fact that it is below the x-axis and is not above the x-axis. So anytime the velocity graph is below the x-axis, that means you're moving backwards. Anytime the velocity graph is above the x-axis, that means you're moving forward. Now with that information, let's see if we can answer these questions. Which way does it move first? Well, it clearly moves left or backwards. When does the particle stop? A particle is at rest whenever its velocity is 0. So the velocity is 0 there, the velocity is 0 there, the velocity is 0 there. So at t equals, looks like 4 and let's see, 3, excuse me. So 3 and 7 and 10. Okay, when does the particle change direction? A particle changes direction whenever its velocity switches from positive to negative or negative to positive. Because if it's positive, that means it's going forward, and if it switches to negative all of a sudden, that means it's going backwards. So it's switched directions. The only point on this graph that it switches directions is right here at t equals 7. Okay, so when is the particle moving to the left? Well, once again, I already answered that. It's going to be every place where the velocity is underneath the x-axis or when the velocity is negative. So we'll answer that in interval notation from 0 to 7. It's moving right from 7 to 10. And when is it speeding up? Now, this is where students get a little confused. A particle is speeding up. I want you to think in terms of a car, and I want you to think about whether your foot is on the gas or on the brake. And this is the speedometer's value. Now, the only thing that the velocity being negative affects is that you're going backwards. But you can see here that the speedometer is moving further away from 0. So that means you're speeding up, but you're going backwards. But you're still speeding up. So you're speeding up from 0 to 1 in union with, well, let's see. Your speedometer now is getting closer to 0, so you're braking, and then you are getting further away from 0, so you're speeding up from 3 to 4. All right, so 3 to 4. And then you're at a constant velocity. Then you are slowing down, but you're still going backwards. You're still going left, but you're slowing down, going left. Then right around here, you are now going to the right, and you're speeding up. You're speeding up because the velocity, the speedometer on your car is getting further away from 0. So you're speeding up from 7 to 9. All right, so your union 7 to 9. And that would be all the places where you are speeding up. So you have to pay attention to that. Okay, when is the particle slowing down? Same idea. It's speeding up here, and then between 1 and 3 seconds, the speedometer is getting closer to 0. So we'll start by saying between 1 and 3 seconds in union with. Now it's speeding up again and constant, and now it's slowing down from, let's say this is 3, 4, 5 to 7. It is slowing down. The velocity is getting closer to 0. So 5 and 7 in union with. Now it's speeding up, and then between 9 and 10, it starts to slow down and get to rest. So bracket 9 and 10. Okay, when is the particle moving the fastest? In other words, when does it have the highest speed? And remember, speed is the absolute value of velocity. Speed does not take into consideration which direction you're going. It just takes into consideration how fast you're going. So the fastest speed that we see is right in this region right here. And so between, let's see, 4 and 5 seconds. When is the particle moving at a constant speed? Well, same answer, between 4 and 5 seconds. Graph the particle's acceleration. All right, so acceleration is the derivative. So let's write this out. Acceleration is the derivative of the velocity. Another word for derivative is slope. So it is the slope of the velocity graph. So let's see if we can calculate the slope, and let's see if we can graph the acceleration on the same axis. Well, it looks like the slope here is -1, so we're going to graph a constant line of -1. Looks like the slope here is up 1 over 2, so looks like it has a constant slope of 1/2 here, so we'll graph that. And then this has a slope of, let's say, 1, 2, 3, 4, down 4 over 1. So that's going to have a slope of -4. So 1, 2, 3, 4. So we'll put a little line there. Now, this has a slope of 0. So we'll just put a line right there. That's not a line. Put a line right here. There we go. And then we have a slope of, let's say, 1, 2, 3, 4, 5, 6, 1, 2, 3. So up 6 over 3. That's up 2 over 1. So that's a slope of 2 for these this time period. So slope of 2. And then another slope of 1. And then a slope of, let's see, -3. So that is the acceleration graph. It's just a bunch of constant lines that represent the slope of the velocity graph. Okay, finally, part K says graph the particle speed for 0 to 10. And we know speed is nothing more than the absolute value of the velocity. So basically all it does is that if the velocity is negative, it just flips it up and makes it positive. And so if it's positive, it stays positive. So that's going to be there and then there. And then that's going to go all the way up to, looks like 4. 1, 2, 3, 4. There we go. And then it's going to be another line there. And then this is going to basically turn into that. And then the rest of it just stays the way it is because it is already positive. So that would be the speed. Speed is just the absolute value of the velocity.